Thank you everyone for joining this part 2 on recommender systems. We're excited to have a new person joining us, not new to Blueprint, but new to the series. So I'm just going to give a quick intro about who I am, kind of housekeeping tips, and then I will pass it along to the data science specialist. So my name is Ruthie Sedanayaka, and I am on the marketing team here at Blueprint. And I just want to, welcome you to the webinar. We did have a part 1. If you did miss that, go ahead and hop on to our YouTube page or our social media pages. We have all of them posted on there as well. And we have a very special webinar planned out for you today. If you have any questions throughout this event, you can always just add it into the chat and we can respond to you there. If you have any questions specific to what the presenters are going to be talking about, you can add that into the Q&A section. And if you don't want to show your name, that's totally fine. You can submit a question as an anonymous question as well. So if you have not heard about Blueprint before, Blueprint is a data intelligence firm, and we're primarily located out of the greater Seattle area, but we have employees all around the world, and it's pretty cool. We focus on customer experience and intelligent supply chain in retail, manufacturing, technology, and the federal government, and we enable digital transformation, offering technology solutions that build a digital culture, make employees more productive, and improve satisfaction, and ultimately increase revenue. So if you'd like to learn more about Blueprint, you can visit bpcs.com. But right now, I'd love to introduce you to two of our speakers for today. So first, I'll have Wes go ahead and introduce yourself, as well as kind of what the data science practice at Blueprint looks like.
Yes, hi, thank you, Ruthie. So as Ruthie told you, we're an up-and-coming data science group, and we're very excited to be here. This is the second in a series of webinars. We might even go to 4 of them, but certainly we'll go to 3. The first one was about how you use attribute similarity in systems in building a recommender system, and we showed an example and talked through some of the background and infrastructure all about recommender systems last time. And this week, we're going to follow up and do a presentation talking about another way of building recommender systems and other techniques that are very important in doing that. And that we're going to be talking about customer clustering and personalization. I should say I'm sort of a principal data scientist at Blueprint, and Aaron is one of our up-and-coming, very exciting new data scientists that we have. And he's based out of Romania. And so, Aaron, why don't you go ahead and introduce yourself and go ahead.
So, hello, everyone. I'd like to say that I'm thrilled for anybody that is joining this webinar. My name is Arin Toacă. I am based in Romania, which is in the EU, part of the Blueprint team. I have about 4 years of experience in the data science, machine learning, AI field. And today I'll be speaking about what Wes has also talked about, recommender systems. And in this webinar specifically, I'll be speaking about recommender systems that help with customer segmentation.
Awesome. Thank you, Aaron and Wes. And Aaron, take it away. And quick reminder to everyone, if you have questions for Aaron while he's presenting, you can add it into the Q&A and we will go through those questions right after.
Okay, great. So let's dig in. As I've said, this webinar will not be very technical, so don't worry if you don't come from a technical background. We will be speaking about concepts, not tools, so I won't be showcasing any code, but I will be showing a demo, and I will be talking about everything that you need from any type of platform to build a recommender system. So let me explain a bit what's going on. I'll just try to, yes, great. So recommender systems are primarily used by item serving platforms of any kind to serve items to users. These items can take many shapes, and the recommendations can also be served in many different ways. But the main problem that recommender systems solve is they kind of curate the items that the platform has so that the users are not hit by analysis paralysis, so to speak. So they have a positive experience with your platform. So you as a platform, or if you're part of a platform, need some sort of strategy to acquire users and convert them to permanent users and keep them there. So you don't want your users to leave. You want to provide a positive customer experience with your platform. So this is where recommender systems come into play. This is the strategy. So you want to create from the data that you already have a way of targeting recommendations to the right users. So you have basically different strategies for existing users and different strategies for new users. So let's start with the new users. For new users, you want to figure out as fast as possible to which archetype they might adhere to. You want to figure out what type of user that user might be, what kind of behavior they might have, so you can recommend the best items for them. You want them to engage with your platform and find the recommendations that you give them meaningful. But you have limited interaction history for them. For your existing user base, you want a recommender system that gets every user, understands them, and can give them good recommendations based upon their interaction history. So to do this, you want to maximize user item interaction. This is a score that you wish to maximize, and it can be encoded in many different ways, depending on the domain of your use case or platform. For retail, for instance, like on Amazon and other such platforms, reviews can be thought of as explicit ratings that can be added to this interaction score. Adding to cart and purchasing the item can be also be a factor. On more social media oriented platforms such as Facebook, likes can be contributing to this interaction score, comments as well. On YouTube, it can be watch time, likes, and so on. So these types of user item interactions can take many different shapes and forms, but the only thing that you actually need is to have some way of encoding the history of the users and the items in a digital way. So as long as you can chunk them in a database and the interactions that they have, that's all you need. So I've said you need different strategies for existing users and for new users. And for new users, you do not have an interaction history, but for existing users, you do. So if you have an interaction history for the user, you can leverage that and create recommendations for them and kind of create this nice positive feedback loop. What the positive feedback loop is basically a way that increases the components that are part of it. So for example here, say we have an interaction history for this existing user. And with this interaction history, we can create recommendations. These recommendations, since they're based upon the history of the user, are good enough to increase the likelihood of that user of engaging with the platform. And if the user engages with the platform more and more, the interaction history grows, and that in turn improves the recommendations. So this is the ideal place you want to be at with your system for every user. But of course, things aren't so clear-cut for new users. So for new users, it's much more challenging to do this since you do not have an interaction history of that user, and you need to kickstart this process with some initial recommendations. And this is the meat of this webinar. we will be focusing on these new users and trying to understand them. So this is why I want to explain to you why sign-up information matters. As you might have seen on a lot of platforms, they ask for a lot of information out of you, or maybe they try to gather that information through your location data of your phone and things of that nature. And that is very useful for figuring out what type of user you might be. Also, this is used by platforms such as Facebook, and maybe you've noticed that Spotify and platforms that do not have access to that much data might ask you to sign up with Facebook. So Facebook can provide that information to these platforms and create some initial recommendations. And the missing puzzle piece, so the flow of what we're trying to achieve looks sort of like this. So for a new user, you have some sign-up information or information that you've gathered from tertiary sources, such as age, location, and maybe something else. You can ask questions of the user. Netflix did this, for instance, at the beginning of their platform. They asked of their users what kind of movies do they like, what genres, and they based their recommendations upon that, since they didn't have that much data at the beginning. So if you're an up-and-coming platform, you might need to do this as well. So you feed this information to something called a user archetype estimator. And this user archetype estimator basically tries to figure out, based upon previous data, to which archetype this new user might belong to. These archetypes are built from the data that you already have of your users. So say you have 100 users, that's more than enough to build these archetypes. And based upon these archetypes, you then can create some initial recommendations that are relevant and can create that positive feedback loop that I've talked about. So the first thing that you need to do to create this whole flow is to build user archetypes. User archetypes are based upon the similarity of users. So similar users will consist of the same group, and these groups will form the archetypes. But we first need to understand the similarity between users. This will be an objective metric that will be extracted by the recommender system. So we will need to dive deep into what the recommender system is, understand what it does, so we can understand this similarity metric and interpret it correctly. So the primary goal of a recommender system is to figure out the best item that it can recommend to a user based upon the interaction history of that user. And one of the ways recommender systems can do this is by figuring out attributes for a user. So for instance, in this example, you can see that the recommender system has learned that this user is thrifty and they like tech. And based upon that, they find an item that fits that criteria. But things are not so simple. Actually, the attributes that are learned from the recommender system are only machine understandable. So they're only numbers and they don't have any labels. And we need to kind of extract relationships between these attributes and the human understandable attributes, the ones that we, with our human brains, understand, such as location, age, and other things that we can gather from the users. So one of the things that you need to know to correctly understand the whole system is how does the system learn these numbers for the users? And it does this through something called machine learning. You've probably heard a lot about machine learning. It exploded in popularity for quite a few years now. Google and Microsoft and all the big tech companies do a lot of research in this field, and it's advancing very, very rapidly. But for our use case, the data that we need to feed to the machine learning model, also called a neural network, is the user item association and the interaction score, which can be computed, as I said, in many different ways from many different factors. Based upon this user item association and the interaction score, the network tries to guess the interaction score, and it compares the predicted interaction score with a true interaction score. Based upon this comparison, the neural network then adjusts its parameters with machine learning, and it tries to give the best prediction it can. So the way that we evaluate and see the progression of the neural net is through something called the loss function. And the loss function simply is the difference between the prediction and the truth being the data in our data set, and the prediction being the guess that our neural net does. And our goal, of course, is to make this difference as small as possible. So we want a loss function that's very small. So to say it a bit more mathematically, what we want to do is to minimize the cost or loss. And there are multiple parameters that you can choose. The most important ones are the learning rate and the epochs. So as you can see here in this plot that there are a multitude of arrows. So this is basically the journey of the neural network of adjusting its parameters, and it needs to find the best loss. The best loss is not known beforehand. And a good analogy here would be an explorer in a desert that tries to find an oasis. So it needs to wander around in a space, maybe sometimes climbing up hills and sometimes descending them, in hopes of finding the oasis. It knows that this oasis is further down somewhere, but not every descent guarantees that the oasis is there. So it needs to explore the space. The arrows themselves, the number of them, is the iterations that the neural network does through the whole data set. So one iteration is one arrow, and this arrow is called an epoch. You can also think of this as the time you give the network to adapt to the data set, to model through the data set. This is given by compute constraints. Maybe you want to train it as fast as possible on the cloud, since sometimes it needs a lot of compute power. And that is, of course, limited by your budget. So besides the epochs, you can also tune the learning rate, which is the magnitude of the arrows. This is sort of like how much should the neural network adapt based upon the observations that it has seen in the data set. The learning rate can be constant, a constant number, but it can also be adaptive. So the arrows change in size based upon how much the loss increases or decreases. The direction of the arrows is given by something called the gradient. And this is kind of the mathematical backbone of the whole operation. And this is given by some fancy math and partial derivatives, but basically it gives the direction of steepest descent. Okay, so these are the components, but you need to choose them. So there are some pitfalls that you can encounter in your machine learning training, and they can be frustrating if you don't understand the whole thing. So for instance, you can have too few epochs. Your machine learning model is not being given enough time to train. Maybe everything else is all right, but you don't give it enough time. So the loss may actually increase before it decreases, and you've only observed that it increases and you don't know what to do. The answer would be to increase the epochs. Another thing that you might notice is that you've given the network maybe a full week to learn your data set, but it didn't reach a good enough conclusion. The loss is still big. That may be because the learning rate is too low. So there is enough time, but the magnitude of adjustments of the neural network parameters is very small. So that's also frustrating, but can be diagnosed in this way. And the weirdest behavior that you can encounter is when you monitor the loss, you can see that it's increasing and decreasing wildly. And from epoch to epoch, you don't see any progress. That can also be because the learning rate is too high. So the model adjusts itself wildly all over the place and may never find the oasis. Okay, besides these pitfalls, there's another tricky thing that you need to take into consideration, and this is equally as important, but a bit more tricky to diagnose, is something called overfitting. and that is why you need to split your data between training and validation. What overfitting is simply a way that machine learning models sometimes learn to cheat by simply learning every user item association in our case, and not actually understanding the user and the item association. So because it has learned these associations by heart, it doesn't generalize to new user item associations. And so you need to hold out part of the data only for evaluation purposes. You do not allow the machine learning model to train, to learn from that data. A good analogy would be a student that has some learning material, which in our case is the training set, but it also has an exam at the end of the course, which is our validation set. And in this case, we are the professor that looks at the machine learning model and it sees whether it has performed the way that we need it to. I also talked about the fact that recommender systems are of multiple types and that we are implementing the specific type of recommender system. The type of recommender system that we're implementing uses something called matrix factorization. And this is just a fancy way of saying that we try to approximate matrices for all the users and all the items to give a predicted interaction score between each user and item. So let me walk you through this diagram a little bit. Say for user 1, we have chosen to learn 3 attributes for each user. So user 1 has attribute 1, attribute 2, and attribute 3. This in turn means that each item has an attribute as well that we've learned of it. So attribute 1, attribute 2, attribute 3. And the combination between the attributes of the user and the attributes of the item gives us the predicted interaction score between that user and item. They are arranged as matrices for computational reasons more than anything else, since matrices are built to be very fast to compute on GPUs and CPUs in the modern computer. And now that we have these numbers for users, we can group them. And I'll explain exactly how you can do that here. Say we've told our system to learn 2 attributes for our user. And so our user can be plotted in a 2-dimensional space. And say we have 2 of these users in a 2-dimensional space. And so the distance in this space tells us the information that we need. So if the user 1, X in this case, and user Y are very far apart, that means they're very different in the kind of behavior that the recommender system predicts they'd have. And if they're very similar, that means they have similar tastes, and they're very likely to be part of the same group. Once you have these users as points in a space, you can group them. You can group them with algorithms called clustering algorithms. And these groups are then the building block of our archetypes. So these groups and archetypes can be thought of as interchangeably in our context. The type of clustering that I've chosen to show in this presentation is pretty straightforward. It's called k-means clustering. And the only parameter that you have to choose for this algorithm, which also falls in the machine learning family of models, is k. So k is the expected number of groups you expect to find in your dataset. This is something you have to choose, and I'll talk about this in the following slides. But in step 1, let's say that we choose k equal to 3. So we expect to find 3 groups in our dataset. Then in step 2, random points are assigned as cluster centroids. Cluster centroids is just a fancy way of saying the centermost point of each group. Then in step 3, we assign the rest of the points based upon their distance from the cluster centroid. Then in step 4, we compute the mean of these groups. So this is the new cluster centroid, the centermost point of each group. And then in step 5, we reassign the points to clusters based upon their distance from the cluster centroid. So we do this multiple times. We compute a new mean and reassign the points. We compute a new mean and reassign the points until the points can no longer be reassigned to new groups. So the color of these data points no longer change. For this example, we didn't need to do this multiple times. It's pretty straightforward. So we ended up with nice groups for the red dots, the orange dots, and the green dots, or users. So another thing that you need to understand is that k-means can be evaluated through the distortion score. And this distortion score is a way of expressing how spread out the points are from the cluster centroid. So in red, we have high distortion relative to the cluster below. So the points are very spread out, and we're not very confident that we found the true cluster centroid. In green, we have a low distortion, so the points are very tightly packed, and we're very confident that we found the right cluster centroid. Another thing that you need to understand is the fact that increasing K naturally decreases distortion. I have two extreme examples here. One of high distortion. The highest distortion that is possible of any data set is a K equal to the number of points in your data set. So for instance, here, K equals to 1. So every point is part of the same group. So they're naturally very spread out. And the example below, K equals to the number of points in our data set. So of course, each point is its own cluster centroid. This is also not very useful in any of these scenarios, since you can't have only one archetype or n archetypes for each data point. So the recommendations wouldn't be relevant absolutely at all. So you need to find a sort of sweet spot for this K, and I'll be speaking about this in the next slide. So we need to choose this K, and one of the ways that you can choose it is through the elbow method. And the elbow method is basically you plot multiple values for K, and you plot it, the distortion score, against the time it takes for the algorithm to reach the right conclusion. And you look at this distortion score against this time to fit, and you try to identify a point where the distortion score decreases only slightly, but the time to fit increases sharply. Once you've identified this point, it's very likely that this point is the optimal K that you need for your data set. Once you have these groups, you've trained k-means, you've chosen the right K. You need to understand what these groups mean. You need to understand what these groups mean to bridge the gap, as I've told in the previous slides. So you have the user, you have their sign-up information, and with the help of the user archetype estimator, you can say with pretty high confidence that the new user is part of a certain group, say for instance, group 1. And this means that this user is very likely to have the similar taste to the people in group 1, since we've noticed that people in that group have similar sign-up information to this user. The way that you bridge this gap, the way that you build this user archetype estimator is through something called a classifier. And the classifier basically figures out through machine learning as well to which class a data point might belong to. So say maybe a good example would be something like a dog or cat classifier, where you know that the image is either a dog or a cat, and the classifier figures out if it's a dog or a cat. But in our case, the classes are actually the groups that we've identified, or the archetypes. And ideally, you'd like to understand why the classifier reached the conclusion that it did for that data point. So we want to ask why the classifier took that decision. And answering this why, there's a trade-off involved in this, because the more complex the classifier, the more accurate and precise it is, so it's likelier to be right. But then the rules that it has, they're very complicated and hard to understand. So us as humans have no chance of understanding it. But if we choose a simpler classifier, it's usually way more explainable, since the rules are simpler, but then the predictions are not as accurate. So the type of explainable classifier that I've chosen to show is a dog or cat classifier, as you can see here. And we ask, say for instance, if the data point is a dog or a cat, as you can see here in this simplified decision tree. If it barks, then it's a dog. If it doesn't bark, does it purr? If it does, then it's a cat. If that isn't also the case, then we don't know. So the class is other. So decision tree tries to narrow down to which class a data point might belong to. But let's give a more pertinent example for our use case. So it might look something like this in practice for the user archetype estimator. We ask whether our user is older than 30. If they are, we ask whether they bought hiking boots. And if they did, are they from the West Coast? If they are, that means they're from group 1 with high likelihood. If they're not from the West Coast, but they did buy hiking boots and they're older than 30, that means they're from group 2 with a high likelihood. If they're younger than 30, did they buy pre-workout? If they did, then they're from group 3. After you train this decision tree, you can then do some investigative work of a sort and look at the way these features are organized as well. So the topmost attribute is the most important. In this case, it's the age. And further along down you go, the less important the attributes become. So you can look at this decision tree, and you can also look at the group as a whole. So you can look at the items that the group has interacted with. And based upon that, you can reach reasonable conclusions. So for group 3, we can notice that besides this decision tree, where people are usually younger than 30 and they buy pre-workout, we've noticed that they buy a lot of gym equipment, like tank tops and lifting straps and stuff like that. So then we reach the natural conclusion that they're mostly people that can be considered bodybuilders. For group 2, we noticed that they bought maybe a lot of hiking gear, but no gadgets of any sort. So that means they might fall into the category of old school hikers. And for group 1, say we noticed that they buy a lot of sports watches and other tech gizmos, but also hiking equipment. So then we can kind of figure out that they're sports enthusiasts that also like tech. Okay, so you have these labels for the groups, and with this information, you can then give tailored recommendations for people that might fall into these groups, people that you have limited interaction history for, but you can pretty confidently say, based upon the sign-up information, that they're part of these groups. So now you have these tailored recommendations for these new users, so you can make them engage with your platform. But moreover than this, now that you understand the groups that are part of your customer base, you can maybe take all sorts of business decisions. Maybe you can look at them and their distribution geographically. Maybe you can create tailored ads for all the groups. Maybe you'd like to cater to some sort of audience that doesn't fall in any of these groups. You identify there's a need for more inclusion. And of course, this is the type of value that the recommender systems can provide to you and your platform. So I've also, before going on to the summary, I've also have a little demo that I'd like to show you here. Let's start from the beginning. This is built from a US e-commerce dataset, which is called the Superstore dataset. It's publicly available. It's based upon US e-commerce data, and you can see some distributions of item quantity, of purchases, and the profit by state and also by city. Also, the top spenders are here. I've chosen to plot item quantity because I think it's a good, simple metric to measure the interaction score. So if a person bought 8 toothbrushes, that means they really like toothbrushes. And if they didn't buy as much of an item, that means they didn't like it as much. Also, you can look sort of behind the scenes at the similarities between users. Here, I've chosen to tell the recommender system to learn 3 attributes for each user, so we can plot them in a 3-dimensional space. Then I've figured out through the elbow method that we have 9 clusters here, and you can see the cluster distribution here. You can see that the groups are tightly packed and well separated. And that means that the k-means algorithm has did a great job with this data set. You can also look at the item attributes here as a more of a sanity check of a sort. So you can look at maybe an LG Exalt is likely to be bought by the same type of user as a data binder with storage hooks. So this is kind of important, that these items aren't similar in the traditional sense of a phone is similar to another phone, but they're similar as in they're likely to be bought by the same type of user. You can also look at the geographical distribution of the clusters here in the US map. The data is not very precise since we only know the city of the customer. And you can see here that the coasts have maybe a different distribution than further inland, which is kind of interesting. The new user estimator is illustrated here. Say you ask different questions about your user, or maybe you gather this data through other sources, and you can predict to which cluster that new user might belong to. You can also see the decision tree if you want to do that investigative work that I talked about. Then, if when you identify the cluster a new user might belong to, you can feed them recommendations. Say we've identified that the user is from cluster 2, and then we can feed the items that have the highest interaction score with the users that are in this group. And say the top recommendations for people in cluster 2 is a Logitech wireless headset. We can also look at the percentage of categories that this group is interested in. So they're mainly interested in accessories and art. So to kind of summarize what we've talked about here is we've talked about strategies for user acquisition and retention. We've talked about the inner workings of the recommender systems, how it works with machine learning, and how it helps you with your use case of growing a platform, how these recommender systems learn from user behavior, how we can group these users together by behavior with the user attributes that I've talked about, and how we can understand these groups based upon demographic segments or the attributes that we get from sign-up. This is pretty much it. This is the whole webinar. I hope you've stuck with me so far. I hope you enjoyed it, and any questions are very welcome.
Awesome. Thank you so much, Aaron. We did have a couple of questions come in, so I'm just going to read them out to you, and either Wes or Aaron, whoever would like to take them. So the first one is, can a person be a member of more than one group?
So the answer to this question is no. For this type of system, we want the user to be unambiguously classified to a single group, so we can manage the way that we understand the users and have a simple but clear-cut overview of our customer base.
Awesome, thank you. Next question we had is, in retail, we often have a lot of new users. How do I know when to recreate the user clusters?
Okay, so this is an interesting question. So say you have a lot of users that are joining your platform. You can recreate these groups as much as you'd like, but there's some effort involved in investigating basically the cluster groups as human understandable attributes. So when you want to give them labels, it's very difficult if the clustering algorithm simply changes. And you need to take that into consideration.
Awesome, thank you. And the last question I have on here is, I see the demo had 3 user attributes. Is this a normal number, or would we expect more or less in other settings?
This is something that you need to explore with your data set. So for our use case, 3 user attributes was enough, but maybe for your use case, you need to choose more. And the only way you can figure this out is through going through the whole process with different user attribute numbers.
And Wes, you're on mute as well.
Apologies. To be fair, the choice of 3 was for pedagogical purposes as well. It's easy to visualize a 2-dimensional or a 3-dimensional set of numbers there. It gets much harder if you get to 7 or 8 or 10 dimensions, but it can very often be lots and lots of attributes.
Great, thank you. Any other questions that we have? I'll give you a couple seconds for any more questions to come through, and then if we have other questions that you'd like to ask outside of this webinar, you can always email us at info@bpcs.com, and we're happy to answer them for you. You can also connect with us on social media, on LinkedIn. Any of us are on there as well. And we will be starting to promote our third part of recommender systems for retail. So if you would like to join that one, we would love to have you at the next one as well. And we will be posting that on our website, as well as all of our social media platforms. So be sure that you're following that as well. I don't see any more questions that have come through, so I guess we can wrap things up. I want to say a quick thank you to everyone for joining, and a big thank you to Aaron for going over all this really great content. And Wes, thank you for joining us as well. And we look forward to having you all on our next part of the series. Thank you everyone for joining, and have a great day.
Thank you. Bye-bye.
Have a great day, everyone.